Okay, how's everybody doing this morning? Good, all right. So, yeah, a little chilly still. First of all, welcome back to everybody who has been separated for the last 5-10 classes or so. It's good to see you all again. I know. Yeah. Right? Well, I know, yeah.
They think vacation started already?
I guess, yeah.
Waiting at the classroom that you guys used to need.
I think Fred put it. I just didn't want to see me again, I guess. Yeah.
He was like, I have to go back.
Right? Oh, no. Don't make me. All right. So today we're going to start with a quick review of capacitors and inductors. So if you were in my class, we talked about this last time. If you were in Fred's class, we probably talked about this about 5 classes ago. But I still think it's a good thing to review. Plus, Fred brought in this super cool demo capacitor here. So I think this is well worth a few minutes of explanation. And you can all check it out too. So we're going to start with that. And then we'll go on to our main topic today, which is RC circuits. So RC stands for resistor capacitor. So we'll talk about what they are. Really, they're just a circuit with a resistor and a capacitor. But there's a couple configurations we can look at. We'll talk about why they're important and how they work. And then we will look at the charge times for RC circuits. That is how long it takes to charge up the capacitor in an RC circuit, and what it means for that capacitor to be fully charged. And then for our lab today, we'll actually get to build an RC circuit, and we'll measure the charge time. So in class, we'll learn how to calculate those charge times, and then we'll also get to measure those in our lab. So I'll show you how to build that circuit and how to use the function generator and oscilloscope to measure those charge times. So that's what we'll be working on today.
Is this going to be a particularly long lab?
No, it shouldn't be too long. Yeah. So any questions before we get started? All right. So then let's start with our review of capacitors and inductors. So we said that a capacitor is just 2 plates of metal separated by a thin layer of insulation. So the way that a capacitor works is that you attach a voltage to it, a positive voltage on one side and a negative voltage on the other side, and then that pushes these negatively charged electrons onto one side, one of the plates, and then those attract positive charges to the other plate. And then when these charges are close to each other, they are attracted to each other, almost like magnets, so that even after you remove the external applied voltage, these charges still stay on those plates, and that capacitor stores energy that way. And then later on, if you provide a path from one side of the capacitor to the other, even through a load, the electrons will try to move from one side to the other and balance the charges out, and that way you can use that energy from the capacitor to do something useful, like turn a motor or turn on a flashlight or something like that. Okay? So we said that this material, this insulation between the 2 plates, is called a dielectric. And there are 3 main factors that affect how much capacitance a capacitor has. In other words, how much energy it can store. Anybody remember one of those factors? Okay. Well, yeah.
I feel like I might be thinking the question wrong, but like the type of metal that you're using?
Almost. I mean, it might have a small impact, but yeah, the type of dielectric actually has a greater impact. So that the type of insulation between them, yeah. So So that's definitely one of them, the dielectric material. What was another one? Yeah. Exactly, the size of the plates. These plates are holding the charges, so the bigger the plate is, the more room you will have to store those charges. So the larger the plate, the more capacitance you have. So that was another one. Yeah. Yeah, how close they are, the distance between them. Exactly, yeah. The closer those plates are to each other, the stronger that attraction will be between the positive and negative charges. So the more capacitance you will have. So the distance between plates. So those are the three main factors that affect capacitance. So any questions about that? Okay. And then we also talked about inductors. So we said that an inductor is just a coil of wire, and sorry, before we move on, I wanted to show off this super cool variable capacitor that Fred brought in. So this capacitor is called a variable capacitor or a tunable capacitor because you can actually change its capacitance by turning this knob one way or the other. So the way that it works is that these metal fins that you see here are the plates of the capacitor. So this is essentially like having several capacitors all stacked up next to each other. But this one set of fins on the top is like, say, the left-hand plate, and the other set of fins on the bottom is the right-hand plate. And so when you turn this knob, it actually moves the fins so that they overlap more or less. So changing the overlap is kind of like changing the size of the plates. It's essentially changing the area that overlaps between the plates. So when you have more area overlapping, it's like having bigger plates, so you get more capacitance. If you have less area overlapping, that's like having smaller plates, and you get less capacitance. So
Wouldn't it be the equivalent of 2 and 3? Because it also kind of, if you have like a piece of metal going in between it, it makes it so it's, the distance is shorter. Like in the case with the nail.
Well, so when I'm talking about the distance between the plates, I'm talking about like the spacing between them. So farther apart would be bigger spacing, closer together would be less.
Yeah, and if you were to put a piece of metal between it, would it help it at all?
If you like stuck a separate sheet of metal in between there,
Yeah.
I don't know. I'm not sure. I would have to think about that. So I'll pass this around so everyone can take a look at that. The application for this is that, I mentioned briefly in our last lecture that one thing capacitors can be used for is called a tank circuit. And a tank circuit looks like this. You've got a capacitor on one side and an inductor on the other side. And the cool thing about this tank circuit is that it resonates at a particular frequency. In other words, it kind of amplifies that particular frequency, and other frequencies that are not that resonant frequency, the other ones kind of are attenuated. So this tank circuit amplifies one particular frequency, and that frequency depends on the size of the capacitor and the size of the inductor. So if you have a variable capacitor like this, and you put it in a tank circuit, you can change that capacitance, and so you change the resonant frequency of this tank circuit. And we said that these tank circuits are really useful in things like radio applications, because when you have a radio, you're trying to tune in one particular frequency. In other words, you want to amplify that one frequency and attenuate the other frequencies nearby. So you can listen to one particular radio station and not, 100 radio stations all at the same time. So this type of capacitor could be used in a tank circuit where you could actually use that to tune in a radio station. So you can adjust the size of the capacitor, you adjust the resonant frequency, and that's how you change which radio station you're listening to. Okay. So so that's one application. Fred knows all about radios. Fred teaches a couple of classes specifically about radio communication, which are super cool, 380 and 381. Was there anything else you wanted to say about the capacitor or tank circuits?
You did a great job. That's anytime you tune a radio, that's what you're doing.
Yeah.
The other thing is, those guys got really smart. They made something called a varactor.
Yeah.
So you might tell them that there's such a thing as an electronic capacitor.
Sure. So this one that we're passing around, you can see it's super cool. It's mechanical. You adjust the capacitance by actually moving metal parts so they overlap or don't overlap. But you can see that it's kind of bulky. You wouldn't want to have that inside of a cell phone, for instance. It might not fit in your pocket very well. And also, if you want to change that, you actually have to physically turn something. So along the way, people decided, well, it might be kind of helpful if we could have a tunable capacitor that was smaller and electronically controlled. So that's a varactor, like Fred was talking about. That's actually, it's kind of a special way or a special type of diode, a special way to use a diode. So you can use diodes in a special way as tunable capacitors, and then they're still in a tank circuit like this, and they change the resonant frequency just like before, and you can tune in different stations. Yeah?
Can you say offhand how to determine the resonant frequency of a particular tank circuit?
Yeah, there's a formula for it. I can't remember it off the top of my head. It's like one over the square root of 2 pi LC or something like that. Am I getting close? Do you know?
2 pi square root LC.
Oh, okay, thank you. 1 over
If
2.
you don't use those every day, you forget about them.
Sure. Yeah, 1 over 2 pi square root of LC. So that would be where L is the inductance and C is the capacitance. That would be the resonant frequency there.
Thank you.
Sure. Yeah. Other questions? Yeah.
I think there's a pencil on there, it says what the capacitance is on the end, I think I put it on there.
Okay.
And it tells you what it is.
Yeah.
And you can actually hook it up to one of our meters and twist it and see the capacitance change.
Yeah, for sure.
Jordan, we talked quite a bit in our little group about, we have the ceramic capacitors that are non-polarized and
Yeah.
polarized electrically.
Yeah.
What makes those blow up when they're hooked up backwards?
Yeah. So
Why are they effective when the ceramics aren't?
So my understanding of that is that the way that electrolytic capacitors are made is that they start with a sheet of foil, almost like we had foil when we made our own capacitors. So, and then remember, you need to have two conductive materials separated by a thin layer of insulation in order to have a capacitor. So with the electrolytic capacitors, what they do is they start with this piece of foil, and then they actually oxidize one side of that foil. So they put it through a chemical process where you end up with this very thin layer of oxidation, almost like rust, or but it's the equivalent for aluminum. Anyway, it's oxide, it's non-conductive, and that becomes your insulator on the one side of your capacitor. And then the other conducting material is a liquid that is kind of impregnated into a cardboard material. So this is the sort of the sandwich that they make, and then they roll that up, and that's the electrolytic capacitor. So my understanding is that if you put say a positive voltage here and a negative voltage over there, then everything works fine, and you get this capacitance. But if you reverse those and you end up with a negative voltage over here and a positive voltage over there, that somehow eats away at this thin layer of oxidation, this thin layer of insulation between those. So then you end up with a little gap there, and that gap allows the electricity to flow from one conductor to the other. And so it flows through that gap very quickly, and it heats up and it explodes. So that's my understanding of it. But yeah. And ceramic capacitors are different because they have a different type of insulation that doesn't get affected by reverse voltages. So, yeah.
So for this, the insulation is just the air around it? Or?
Yeah, that's exactly right. Mm-hmm. Yeah. Other questions? All right. So then let's talk a little bit about inductors. So an inductor is about the simplest component that you can have, because an inductor, every inductor is just a coil of wire. But that also means that every coil of wire is an inductor, whether you like that or not, whether it's convenient or not. So that's what an inductor is. The reason why they are important and interesting is because they allow low frequencies to pass through them, but they block out or absorb high frequencies. So inductors can be used in filters and tank circuits also. So we said that if you have a coil of wire, there is a formula that you can use to calculate its inductance. So say we had a coil of wire like this. The formula for the inductance is L equals N squared times A over little l times some constants. Where N is the number of coils and A is the area, so the cross-sectional area of this coil, and then little l is the length of the coil. So in this case, it would be like that. So you can use that formula to calculate the the inductance of an unknown coil. Now, these constants have to do with like what the coil is wrapped around, and I think the width of the wire and stuff. They can be a little bit finicky. So in practice, this isn't usually used to calculate an inductance of a brand new coil that you've never seen before, but it can be used to compare two different coil designs that are similar to each other. So if you have two different coils and they have the same number of turns, say they wrapped around the same stuff, they're made out of the same material, but one is twice as long as the other, this formula tells you that the longer one is going to have half of the inductance of the shorter one. So this formula can be used for comparing similar coils to each other, or comparing changes in the design. Yeah?
So the formula is pretty much calculating the efficiency of what the coil is doing?
Yeah, that's one way to think about it. Yeah. So how much inductance it has. So yeah.
What's the big L stand for now?
L stands for inductance. Yeah, I don't know why people picked the letter L to stand for inductance, but yeah.
Because they picked the letter I to stand for current.
Right. Exactly. Thank you. There you go. That's logic for you right there.
Where does the unit Henry comes into? How do you figure that out?
So Henry was named after one of the early scientists that worked on inductance. So the inductance is given in henries.
Okay, so that is the unit Henry.
Yeah, so when you calculate the inductance, that would be how many henries or millihenries that coil has.
Okay.
Yeah.
And so the N equals the amount of turns in the
Yeah.
coil.
Yeah. Thank you. Number of turns. Yep. Mm-hmm.
And so when you look at a transformer, if you see the number of turns more than the primary, you know it's going to go up. If it's less, then you know it's going to go down. It'll be a rectifier, right?
So inductors are found in many different devices, including transformers. Yeah. So we said that every inductor is just a coil of wire, and every coil of wire is an inductor, whether we like it or not. And like you mentioned, transformers are just two coils of wire that are close to each other. So each of those coils is an inductor. So yeah, we could measure the inductance of each of those coils, and each one would have its own inductance. Can anybody think of other places where we find coils of wire used in electronics or daily life?
It's everywhere. Clock, phones, not the phone, but the clock, the TV.
Yeah, probably. Yeah, the television.
Just regular springs, right?
Yeah.
Have an inductance.
Spray. Yeah, if you hooked up some wires to them, yeah, some voltage, and yeah, that'd be an inductor also. We also talked about cars. We said that cars have coils in their motor and those coils are used to create high voltages that make sparks in the spark plugs that ignite the gas in a cylinder. So that's another place. And we also talked about electric motors. We said that electric motors include electromagnets, and those electromagnets are just coils of wire. So electric motors have inductors in them too, and they exhibit inductance, whether that's convenient or not. Also, if you got some extra wire just lying around and it's getting in your way, sometimes you might coil that up to make it a little bit more tidy, and that can be fine. But if you have a radio and that's wire that's coming from your antenna, that coiling that wire up might be a bad thing, because when you coil it up, you're making your own inductor. Whether you want to or not, you've made your own inductor. And remember, those inductors block out or absorb high frequencies. Well, radio signals are very high frequencies. So if you put an inductor in the path of your radio signal, you might actually be attenuating your radio signal. So that could be a bad thing. So those are just a couple things to think about. So that's a quick review of inductors. Are there any questions about that? Yeah.
Is there a determination of what sort of frequencies they would block out at what states or what coil? Like how much you would need to like block out a certain bandwidth? I don't know, like high
Right.
frequency, whatever.
Right.
String.
So, yes, there. What happens is that we've talked about resistors in this class, and we've talked about inductors and capacitors. Resistors have a fixed resistance. It's the same no matter what frequency you put into them. Capacitors and inductors actually behave kind of like variable resistors, whose resistance changes based on the frequency that you put into them. So with inductors, the resistance gets higher as the frequency increases. And with capacitors, it's the opposite. The resistance increases as the frequency decreases. So the formula for the gosh, I'd have to look it up again. But the formula for the so we call this changing resistance, we call that reactance. So an inductor has a reactance, and that's abbreviated with XL. That's the inductive reactance. X stands for reactance. And that is like 1 over the square root, or no, 1 over, or I think it's 2 pi times F times L. Am I getting that? Yeah.
One of them has 1 over. One
Yeah.
I get the two mixed up. The
Yeah.
capacitor has 1 over, and that one has.
Yeah.
I think you got it right.
Yeah, okay. So the inductive reactance is 2 pi times the frequency times the inductance. And then the capacitive reactance, XC, is 1 over 2 pi FC. So if you know what the inductance is, you can calculate the reactance at that particular frequency, at a particular frequency. Yeah. Yeah.
So you said the right one is capacitive inductance?
Is capacitive reactance, yeah.
Reactance. And then the left one is what again?
Inductive reactance.
Gotcha.
Yeah. Yeah.
When I've heard the term reactance thrown around talking about radio antennas, but I didn't really understand it before.
Yes.
When an antenna designer is trying to match an antenna's impedance to the equipment that they're using,
Right.
are both of those types of reactance factored into it?
Yes.
Thank you.
Yeah. So yeah, so that's a great question, and it's something that Fred covers a lot more in the radio class, 380 and 381. Yeah. Mm-hmm. So yeah, other questions? Okay, cool. All right, so then let's go on and talk a little bit about RC circuits. So an RC circuit is a resistive capacitive circuit. But resistive capacitive is kind of a mouthful, so everybody just calls them RC circuits. So really, an RC circuit is just what it sounds like. It's pretty simple. It's a circuit that involves a resistor and a capacitor. There's two main configurations that it could be in. You could have a resistor up here like this, your input voltage there, and then a capacitor down here going to ground, and then your output voltage there. Or you can switch around the places of the two components. So you could have your input voltage here, and then your capacitor up here, and then your resistor down there, and then your output voltage there. Okay? So that's what resistive capacitive circuits are. These are important and interesting for a couple of different reasons. First of all, and we'll be talking about this more today, is that in these configurations, the capacitor takes a certain amount of time to charge up. And we can use that charge time to set the timing on certain things in our circuit. So for instance, if we want to set the timing on a blinker in a car, we want it to be on for a certain amount of time and then blink off, and then on and off and on and off. We can set that time using an RC circuit. So we can have the blinker go on while the capacitor is charging up, and then when it gets to a certain level, we can start discharging that capacitor and make the blinker turn off while the capacitor is discharging. So we can use the RC circuit to create timing in our application like that. And as we'll see in a minute, we can choose the amount of time that it takes for this capacitor to charge up based on the capacitor value and the resistor value in our circuit. So one useful application for these circuits is in timing applications like that. Another application for RC circuits like this is filters. Now, we talked briefly about filters when we were discussing our fiber optic communicators. We said that there were some filters in those communicators. And so these are two different types of filters that you can build for electronic circuits. And the way that the filters work is that these capacitors allow high frequencies to pass through them, but they block out or absorb low frequencies. Another way of saying that is with this reactance that we were talking about just a minute ago. As the frequency increases, the reactance decreases. And so it's easier for high frequencies to go through. And as the frequency decreases, the reactance increases, and it makes it more difficult for those frequencies to go through. So the result is that with a circuit like this one on the right, you've got a capacitor in the path of the signal, and that allows high frequencies to go through to the output, but it blocks or absorbs low frequencies. So we call this a high-pass filter. Whereas over here, the capacitor is going to ground. So high frequencies have a path to ground, and they don't get through, whereas low frequencies can't go to ground. They're blocked from ground. So low frequencies pass through to the output. So we call this filter a low-pass filter. Okay? So electronic filters are another application for RC circuits. Okay? So those are a couple of the reasons why we are interested in RC circuits. for timing applications and for filter applications. So, what's that?
Do the exact same thing, but just simulating with code? Like,
Sure. If you built a circuit like this in Multisim, you could run a simulation and see the how the output behaves.
no, I mean, because a large point of resistance capacity, like RC circuits are just for timing, you said.
That's one application for them, yeah.
And could you simulate that, which is writing a code that could turn on lights at a certain amount of time?
Sure. So, yeah, so in the olden times, there weren't computers in cars and everything, and so and many electronics. So electronics had to rely on analog devices for timing, such as this. But yeah, nowadays many circuits include some microcontroller, and you can have timing delays built in to the code in your microcontroller.
And
Yeah.
a lot of newer cars use that.
Yeah. Yeah. Mm-hmm. So, yep, there's lots of different ways to do it. Yeah.
What's the purpose of the resistor in both these circuits?
I'm glad you asked. We'll get to that in just a second. So, yeah, so that kind of brings us to so how circuits actually work. So, what happens is that in these circuits, the capacitor acts kind of like a big barrel that you're trying to fill up with water, and the resistor is like the hose that you're using to fill up that barrel. So you can imagine if you have a really big barrel, but you have a really tiny hose, it's going to take a long time to put the water into that barrel, and it's going to take a long time to fill up. Whereas if you have a little tiny barrel and you're filling it up with a fire hose, it's going to go real fast, right? Well, it's the same sort of situation here. The capacitor is like the barrel that stores the electrical energy, and the resistor is like the hose that you're using to fill it up. So a big capacitor is like a big barrel. When you have a large resistance, that's like it makes it very hard for the electricity to flow. It's like using a little tiny drinking straw to try and fill up your barrel. So the bigger the resistance, the harder it is to fill that up. Whereas the smaller resistance you have, the easier it is for the electricity to flow, and the quicker that capacitor will fill up. So, so that's the basic principle of how these circuits work. So if you choose a big resistor and a big capacitor, that's going to take a long time to fill up. So that would have a long charge time. Whereas if you chose a small resistor and a small capacitor, that would fill up quickly, and you'd have a short charge time. So that's the way that you can affect the charge time. Now, if you were to look at what happens when you're charging up these capacitors, what happens is that if you look at the voltage over time, say your input voltage looks something like this. At first, it's down here at 0 volts, and then sometime you change it and you put it up to maybe 10 volts. And that's when your capacitor starts charging. What would happen to the voltage on the capacitor is that at first, it would start to charge up really fast because there's a big difference between the current voltage and the input voltage. So it would start to charge up really, really fast. But then as the input voltage, or the capacitor voltage gets closer to the input voltage, the charging slows down. And the closer the capacitor voltage gets to that input voltage, the slower it charges. So what happens is that it goes like this, and the capacitor voltage gets closer and closer and closer to this input voltage, but it charges slower and slower and slower. So theoretically, the capacitor voltage will never actually reach that input voltage, because the closer it gets, the slower it goes. So it just keeps slowing down and never quite gets there. So, so that's what happens to the capacitor voltage when you're charging it up. So you might wonder, well, how can we use this capacitor to time something if it never fully charges? I mean, how can we, use its charge time if it never fully charges? Well, what people have decided over the years is that, okay, it's never going to fully charge, but we can pick some value here and take how long it charges, or measure how long it charges, measure how long it takes to get to that particular charge value. So we can take a value of 63.2%, and we can measure how long it takes for the capacitor to charge up to 63.2% of the input voltage. And we'll call that the RC charge time, or tau for short. So this length of time where it takes to charge to 63.2%, we'll call that tau, or the RC charge time. And turns out there's a convenient way to calculate what that will be. So tau, this RC charge time, just equals R times C, the resistance times the capacitance. Okay, so if you know your resistor and your capacitor, you can use them to calculate what that charge time will be. Equivalently, if you know what that charge time, what you want that charge time to be, say you want your blinker to stay on for 1 second and then go off for 1 second, and back and forth like that, you can use that time to find values of R and C that'll give you that time that you're looking for. Okay? Now, what if we want to know how long it takes to fully charge this capacitor? Well, I already said, theoretically, it would take an infinite amount of time. It'll, take forever. But in practice, you can see that after a while, the resistor or the capacitor value gets pretty close to the input voltage. So it'd be nice to know how long it takes until that capacitor is sort of close enough to the input that we call it, good enough, and we say that's fully charged. Well, what happens is that you can measure how much a capacitor has charged up after various numbers of these charge times. So after one charge time, the capacitor is up to 63.2%. If you looked at another charge time, so after two of these time constants, the charge would be up to about 86%. After three, so let me make a table over here because I'm going to run out of room. So after one time constant, the charge is about 63.2%. After two time constants, it's up to 86% or so. After three time constants, it's up to about 95%. After four time constants, it's at about 98%. And then after 5 time constants, it's at about 99.3%. Okay? And so people have tossed this around for a while, and they said that at 99.3%, you know, that's less than 1% away from fully charged. We're going to call that good enough. So 5 time constants is often used as a good approximation. We say that 5 time constants is about fully charged. Even though it might not be, you know, completely 100% there, it's pretty close. So 5 time constants is often used as an approximation for fully charged. So that's what's going on. That's how we can actually calculate the charge time for an RC circuit. So we can use the resistor and capacitor values to find that time constant tau, and then that's how long it takes to charge to 63%. And if we want to know how long it would take to be fully charged, or good, close enough, we can use 5 time constants to find that. Okay. So any questions about that? Okay. So that's what I wanted to say about RC circuits. So let's go on and do a preview of today's lab. Yeah.
One thing that always confused me, maybe confused these guys too,
Uh-huh.
is every time that goes up to 60, you didn't just make up that 86%.
Right.
63% of what's left.
That's a good point, yeah.
And every time it goes up, it's 63. Because otherwise, I don't know where that the 86 came from, but it's 63% of what's left, and it keeps getting smaller.
That's exactly right. Yeah. So yeah, I didn't mention that, but yeah. So the first time in this first time constant, it goes 63% of the way to the top, and then it ends up there, and then yeah, this next one is 63% of the remainder. So that gives you this next value, and then 63% of the remainder, yeah, each time. Yeah. So that's a very good point.
I didn't mean to interrupt. But
No.
that was one of the questions I always had.
Why all these weird numbers, right?
Yeah.
Yeah, exactly. Yeah, that's where they come from. Thank you. Yeah. Yep. Other questions? All right. So today we're going to do the RC charge times lab. So that starts on page 177 in your lab books. So the first part of the lab talks a little bit about timing circuits. And what we're going to do in this lab is we're going to build an RC circuit and measure the amount of time that it takes for the capacitor to charge. So yeah, so this has a table in there that shows the charges there. And then what you're going to do is you're going to build a circuit that looks kind of like this on a breadboard. And you're going to use these different combinations of resistors and capacitors. And for each one, you're going to measure the time constant. Or first of all, you're going to calculate the time constant, and then you're also going to measure the time constant. Okay? So I've got I want to do one example here with you so that we all know what we're talking about. So I brought with me a 10 kilo ohm resistor and a 1 microfarad capacitor. So let's calculate what that time constant is, and then we'll build the circuit and measure it and see how close we were. Okay? So the resistor is 10 kilo ohms. The capacitor is 1 microfarad. So tau the time constant is R times C, so that's 10,000 ohms. Remember, when you're doing calculations, you always want to convert to raw units before you do the calculation. So I'm not going to leave this as kilo ohms. I'm going to turn that into ohms. So that's 10,000 ohms. And then a microfarad is 0.000001 farads. So in this case, tau should be 10,000 times 0.000001. So does anybody have a calculator? What does that come out to be?
0.01,
Okay,
maybe.
0.01. So that would be, the unit of tau is in time, so that's seconds. So that would be 0.01 seconds. So that would be 10 milliseconds. Does that seem right? Is anybody else getting the same numbers? Yeah. Yep.
I'm just trying to figure out, where did the 10 kilo ohms and the 1 microfarad come from?
Those happen to be the resistor and capacitor that I brought with me.
Oh, gotcha. Okay.
Yeah. So when you're doing it, you'll, for the first one, you'll use a 1 kilo ohm and a 2.2 microfarad and do the calculation that way.
Okay.
Yeah. Yep. Other questions? All right. So this is the time constant that we have calculated. So 10 milliseconds. So then now what we want to do is we want to build a circuit and actually measure this time constant. So we're going to build a circuit that looks kind of like this on a breadboard. So over here on the left, this represents our function generator. So we're going to have a function generator that creates a square wave. And the ground lead from that function generator is going to be hooked to ground, and then the positive lead is going to be hooked to this part of the circuit. The signal is going to be hooked there. We're going to have a resistor and a capacitor here, and then we're going to use our oscilloscope, and we're going to measure this signal right here, which is the input that's coming from the function generator. We're also going to measure this signal right here, which is the capacitor voltage. Okay? So when you build this circuit on a breadboard, the resistor and the capacitor might look something like this. So I like to build my circuits so they look kind of the way they do in the book. So the resistor is across the top here, and the capacitor is going from the resistor to ground. So that's what I got. I've got the resistor here, and then the capacitor going from the resistor to ground. And I'm using this bottom row here as ground because I know that I might have several different signals that have to hook into ground. So when I use this bottom row, I've got all of these holes all along the bottom that I can use for ground. Okay, so that's the components there, and then I want to attach my various signals. So I'm going to first of all attach the signals that come from the function generator. So I'm going to take my function generator leads. I like to hook them onto little jumper wires because that makes it easier to attach them to the board. So I've got this ground lead hooked to a jumper wire, and I'm going to push that into the ground row down on the bottom of the board. Then the signal lead is hooked to a jumper wire, and I'm going to attach that right here to the left side of my resistor, just like it's shown in the lab book. So the signal from the function generator is going to the left side of the resistor there. Okay. Now I'm going to hook up my oscilloscope. So I'm going to take one of the leads from the oscilloscope, and I'm going to hook the I've got the little ground clip here from the oscilloscope, and I'm going to hook that into ground. I'm going to push that into the ground row, and then I'm going to connect the other lead from this oscilloscope, the probe. I'm going to hook that right here where the function generator connects to the resistor. Okay, so I've already got a jumper wire going in right here, so I'm going to connect my oscilloscope right to that jumper wire. Okay, that's the same jumper wire that has the signal from the function generator. And then the other lead of my oscilloscope is going to this point right where the capacitor connects to the resistor. So I'm going to take this other lead from my oscilloscope. Again, I'm connected to a jumper wire, and I'm going to push that right into this spot where the resistor meets the capacitor. So I've made that connection there. And then I'm going to take the ground clip from this oscilloscope lead, and I'm going to clip that onto the ground down here as well. Okay. So now I've got my circuit hooked up, and I've made all the connections. So what I want to do next is that I want to set up my oscilloscope and my function generator so that I can get a good measurement of this signal. Yeah.
What's connected to each wire again? Like, so what's connected on the outside wires?
So like this one?
Yeah.
So this one is going to the connection between the resistor and the capacitor. So this is the lead from the oscilloscope.
Okay.
So
both outside ones would be lead from this oscilloscope, or just the green one?
So the green ones, so this green one is the lead from, one lead from the oscilloscope. This other green one is the oscilloscope and the function generator.
Okay.
Yep. And then the black ones here are grounds. Yep. Okay. So now I've made all the connections. Now I want to hook up my oscilloscope and my function generator so that I can actually measure these charge times. So what I'm going to do here is I'm going to turn on my function generator, and I'm going to put it in the square wave mode. Okay? And we'll talk about the frequency in just a second. Now I'm going to come over and I'm going to look at my oscilloscope. In this case, we want to have two signals on. We want channel 1 and channel 2. So that's the blue and the yellow signal. This function generator has them both on, but sometimes yours might not. If a signal is on and you want it to be off, you can just push the colored button that corresponds to that signal, and that'll turn that signal off. And vice versa. If that signal is off and you want it to be on, you can push that colored button and it turns that signal on. Okay? So you want to make sure you have channel 1 and channel 2 on, and you don't want any of the other channels. Okay? So just channel 1 and channel 2. Now, when you look at your oscilloscope, it might look something like this. So that yellow channel is channel 1. That's the square wave that's coming from the function generator. So you can tell that's a nice square wave, but and channel 2 is the capacitor signal. Right now, that capacitor is not getting fully charged. When it gets fully charged, it kind of reaches the top of that yellow square wave and it levels out. Right now, you can see it's not getting anywhere close to the top and it's not getting level. So what that means is that we need to give the capacitor more time to charge up. And we can do that by lowering the frequency. So if I go to my function generator and I put this in a lower frequency mode here, now when I come back to my oscilloscope, now you can see that the capacitor has time to fully charge, and it gets all the way up to the top of that square wave, and it levels out, okay? You really need to see the capacitor signal level out like that. So once you've got your capacitor, your function generator on a good time setting that allows it to level out like this, you can start to actually measure how long it takes for this capacitor to charge up. And the way that we're going to do that is we're going to use a feature of our oscilloscope called the cursor. So a cursor is something that allows you to make measurements on your oscilloscope. So if we come up here, we have to find the button that says cursor on our oscilloscope. We can push that. And now the type of this cursor right now is shown up here, and the type is off. So right now there's no cursor being shown. If we push this type button, this will cycle through different kinds. Now, the controls on the oscilloscopes might be a little bit different. With my oscilloscope, I just push this button repeatedly to cycle through the different types of cursors. Your oscilloscopes might be a little bit different. I think that with your oscilloscopes, you push the button and then you use a knob up here to select the type of cursor from a menu. Okay? But in any case, we can look at amplitude or we can look at time. Okay? I believe that with the scopes in the classrooms, that amplitude is the best way to do this, okay? So we want to know how long it takes for, well, we want to measure the time constant, right? And the time constant is how long it takes for the capacitor to charge up to 63% of the final value. It'd be nice if we didn't have to do a lot of crazy math to figure out what that 63% is. So what we're going to do is we're going to choose our input amplitude to make our math a little bit easier. So we're going to choose our input amplitude to be 10 volts. In other words, if we look at the input voltage, we're going to make sure that it's 10 volts from the bottom of the wave to the top. In other words, 10 volts peak to peak, because that way we know that 63% is just 6.32 volts. Okay, 63.2% makes the math really easy. Okay, so we want to make sure that we set our amplitude to 10 volts. So let's just back up a minute and make sure that our amplitude is at 10 volts. The way that we can do that is we can push channel 1 here, and we can push the measure button up here at the top. Okay, so right now the peak-to-peak amplitude is at 10 volts because I set this earlier. If it wasn't at 10 volts, you could go to your function generator and adjust that amplitude a little bit to make sure that it was right at 10 volts peak-to-peak. That way it makes your other math a lot easier. Okay? So anyway, now our input amplitude is at 10 volts peak-to-peak. Now we can use our cursors to make some measurements here. So again, we're going to come back up here. We're going to push the cursor button. We've chosen the amplitude type of cursor there. And so now we've got these two lines that go across our screen, these horizontal blue lines. So what we're going to do is we're going to select one of the lines, and we're going to move that so that it's right at the bottom of this wave. Okay, then we're going to select the other line, and we're going to move this around. And what you'll notice here is that there's this measurement that's labeled with this triangle and then V. This triangle is the Greek letter delta, and it stands for difference. So this is the difference in voltage between the two lines. So we want to show a 6.32 volt difference between those lines, because that's going to be the amount that it takes to charge up this capacitor, or for one charge time. So I'm going to move this top cursor down until I get to about 6.32 volts. Okay, so I'm right there. So that shows 6.32 volts. So in other words, when this blue line reaches, or when this blue trace from my capacitor reaches that top cursor, that's where it's gotten to 63.2% of the total voltage. So now what I can do is I want to measure, I want to remember where that spot is right there, okay? So what I can do is I can use this position knob over here on the right side of my oscilloscope, and I can move my signal around so that 63.2% is kind of right in that middle of my oscilloscope. So that this middle line is kind of right there where the horizontal cursor meets my charge line there, okay? So I've got that set up, and now what I can do is I can change over the cursor type to time, okay? Now what I'm going to do is I'm going to move one cursor here to the start of my wave, and then the second cursor, I'm going to move it right to the middle of my line. So now that's right at the 63.2% or so. So that's measuring the amount of time that it takes to charge to that 63%. So that should be our charge time. So now we can look at the delta T here, or the change in time, and that's showing 9.6 milliseconds, okay? So that would be our measured charge time. So we calculated a charge time of 10 milliseconds, and we measured a charge time of 9.6, okay? So we would record those values in our lab book. The measured would be 9.6, the calculated would be 10, and that's how we do that. And then what you would do is you would switch out your resistor and capacitor. You could keep everything else the same, but switch your resistor and capacitor to the next value that is shown in the lab book, and then repeat the calculations and the measurement for those new values, okay?
So you just leave the screen where it was and it just pop up the numbers each time you replace the capacitor?
Well, you might have to make some adjustments because the charge time will be different. So
Okay.
yeah, so you'll have to move your cursors around and do that again. Yeah. Yeah. Other questions? All right. And that's pretty much the whole lab. So you just do that with looks like 5 different values, 5 different pairs, and that's the lab. All right, so then let me take attendance, and then I'll let you go.